function up and down. It goes by page, otherwise it's soft scroll. Yeah.
Okay. So thanks, Adrian, for organizing this, and thank you for inviting me. My name is Ronald. I'm the founder of a small New York-based video research company, Two Orioles. And I'd like to present two of the projects that we're working on, David, the AV1 decoder, and our AV1 encoder, Eve AV1. So first, David. Video LAN released David in September 2018. And that was a collaboration of a couple of companies, us, Two Orioles, and Video Labs, and Multicore, as well as a whole bunch of individual open source contributors. And the goal here was really that we wanted to create a really, really efficient AV1 software decoder implementation to sort of jumpstart platform support, right? Because there's no hardware decoders. We know that they're coming, but they're not there yet. So we're basically trying to fill that gap until hardware decoders make us obsolete. So that was David. Most of you should be familiar with David by now. I mean, a lot of people have been mentioning it and referring to it, but just to give a very quick overview of how fast David is and sort of performance that you should expect out of it. If you decode a typical set of video files using David and you compare the decode performance to that of other open source AV1 decoders, single-threaded will be about twice as fast as libaom and will be about 4 times as fast as GAV1. Multi-threaded, the difference goes more to like 3x to 6x. The GAV1 difference is slightly different from what you might have heard yesterday, and that's because there's different coding tools between our tests and their tests. This is on Haswell, so x86 CPUs with AVX2 optimizations. If you use earlier x86 CPUs, those having SSE3 optimizations, the difference will be a little bit less, but still very substantial. 64-bit ARM results will also be very similar to this. On 32-bit ARM, David is not yet fully optimized, and so the results will be substantially less generous, shall we say. Now that we have a really efficient AV1 decoder implementation, we can actually use this decoder as a metric of codec complexity. And we can use the same files, encode them with different encoders at the same quality, decode them with FFmpeg's native decoder, and use that as a metric of actual codec complexity. And if you do that, you get the results shown here. And what that shows us that AV1 is basically about as complex as HEVC. And that's pretty cool, because a lot of people were concerned about decode complexity, and apparently not really any reason for that. At the same time, though, you can see that AV1 using David is a lot more complex than earlier generation codecs like VP9 or 264. Next, memory usage. So if you use David for decoding AV1, memory usage will be substantially lower than when you use libaom. Compared to GAV1, the difference is basically non-existent in the single-threaded case. And when you enable frame multi-threading, that's when you switch from CPU cores 2 to 3, then the memory usage of David is slightly higher than GAV1, but still quite comparable. And just to give the comparison versus other codecs, again, David looks very good and appears to be basically the best of all of these codecs, particularly as multi-threading kicks in. Quickly, let's look at the implementation complexity, right? How much code did we need to actually get to this kind of a performance? If you go down this list, you will probably notice that most of the code in David is assembly, not actual C code. And that's intentional. Nathan loves to say that David is a bunch of assembly with a tiny C wrapper, and that's basically right. Our philosophy is that the best way to write an optimized decoder is to make it not do anything stupid. And the best way to not do anything stupid is to not do anything at all. So the less C code, the faster it is. Small source code size also translates to small binary size. This is particularly important if you have to carry this as a payload that you have to transmit to users. For example, mobile applications where you have to download a mobile app, or Chrome or Firefox updates where you have rolling updates every couple of weeks. So, and David is substantially smaller in binary size than either libaom or GAV1. So I think that we can sort of summarize this as David is really awesome. I think a lot of people here have given positive feedback on it. We think it's really awesome. We've seen really incredible uptake of David. For example, Chrome and Firefox nowadays use David as their AV1 decoder of choice. We're really happy about that. We hope that other people will continue to consider including David in their products as well. If you use it, please let us know. We'd love to hear it. If you, for some reason, cannot use it and it's because it sucks, we would also love to hear that, because then maybe we can continue to improve it going forward and try to address that. The last slide that I had on David was going to be pain points in AV1 that we found while implementing the codec. My understanding is that Nathan already addressed some of this yesterday. So I'm sort of going to skip over this. And instead of talking about pain points, I just want to say that there are pain points. But overall, from a decoder perspective, implementing AV1 has been quite pleasant, basically. The pain points are minor, and overall, it works quite well. So that's enough about the decoder. I wanted to leave a couple of minutes for the encoder also. So let's switch now to the encoder and talk about Eve AV1. So Eve AV1 is a commercial and a closed source encoder developed by my company, Tutorials. It's the primary use case for this encoder is offline encoding of video on demand content, and then particularly the very high value content. So the content where you're willing to spend a lot of CPU on getting the very best bits per quality outcome out of your encoder, right? And this can either be because it's content that's played a lot, right? Like the Gangnam Style kind of thing, or it's because there's an intrinsic expectation of quality. So promotional content, ads, or just paid content and things like that. And that's where our encoder really, really shines. So I think the classical way that people try to demonstrate that their encoder is great is by showing quality curves. So let's show a quality curve. This curve shows sort of like a representative 1080p clip encoded with all of the open source AV1 encoders or our encoder. And what you can see is that the blue line is further to the left. And right, if you measure the distance is about 20%, right? So we use 20% clips that get the same objective quality. Now, of course, we all know that objective quality is a stupid way because we actually want to look at the video. So you should look at this. Do you think that the left or the right looks better, right? So you can actually visually see this difference also, even if it's a little bit dark. All right, so that was one clip, right? So we obviously run this over many clips, and if you do this over many clips, then the average bitrate reduction using VMAF as a metric is about 20% compared to LibAOM. I'm showing results versus Ravi and SVT-AV1 here also, but I should note that these results are from June. And I know that SVT-AV1, as you just saw in the presentation, has had substantial improvement since June, and so did Ravi. So take those results with a little bit of a grain of salt. Now, the other variable that you see here is average runtime, right? And that's something that so far we don't really talk about. We don't often talk about encode complexity in the video on demand case, but I think we should. So what you can do with this is that you can rerun these experiments at different settings, different speed settings or speed presets for each of those encoders, and then plot out the encode complexity versus the bitrate reduction, right? And then you get the three-variate relationship between encode complexity, bitrate, and quality. And that looks like this. So in this graph, horizontal axis is encoding speed, right? It's basically like the speed preset. And then the vertical axis is average bitrate reduction of the reference, the best one. So if you wanted at the worst speed versus whatever it is that's actually on that point of the graph. And what you can see here is that EVA1 does actually give significant quality improvements over these other encoders, even when normalized for encode complexity. And you can also see in those graphs already that, yes, SVT-AV1 does really shine at the high speed end and has improved substantially since I ran these experiments. then if you take any one of these speed points as a baseline, those are all single-threaded experiments, and you run them multi-threaded, you can also get an idea of how well this encoder scales on multi-core machines over multiple threads, and you can see that the difference is essentially the same. Okay, so that's probably enough about encoder performance. I wanted to keep a couple of minutes, if we have time. Yeah. To talk about pain points, right? So encoder pain points specifically. So when implementing an encoder, especially AV1, stuff gets really slow. And there's basically two things to this, right? There's like, how long does it take me as a developer to implement a particular tool, right? Especially because sometimes you may want to independently implement tools, not just copy what the reference provides. And then secondly, there's of course the actual runtime of the encodes as a complexity. We think that we're getting at a stage where this is getting problematic, and I really like some of the tools that do not exponentially add to the runtime, like the post filters, like Global Motion, and some of the other tools. For AV2, it might be nice to consider removing some of those, especially those that don't appear to give such big gains anymore, like wedges or dual filter, or things that are just not used, like the bilinear filters and stuff like that. And that would help a lot. But the one that I want to spend some more time on is the multi-threading. So as you just saw in Madi's presentation, that one of the methods of multi-threading that you can use is where each superblock row is encoded in its own thread, right? This is basically what VP8 called partition threading. There's something similar in HEVC called wavefront threading, right? In AV1, if you want to do this in a drift-free way, you run into the problem that each of these superblocks can access the superblock row above across the top right edge of the superblock. And that means that the horizontal distance between those two threads is not one superblock, but two superblocks, right? This might seem trivial, but it does mean that the theoretical limits of how far you can scale your multi-threading is decreased by half, and it's for a very unnecessary reason. It's essentially just like an oversight during encoder development, right? If we had put a block on how far you can go across the superblock boundary, we would have scaled ×2. Likewise, talking about frame threading, if you have two frames that are encoded in different threads, and you have one block or one superblock and one thread referencing a position in the reference frame, that is essentially the same point. And because of subpixel motion interpolation, you actually go to the bottom right, into the bottom right block of the next row, of the next loop restoration row in your reference frame. That means that that reference frame needs to have its loop restoration processing proceed at least to the point to the right of that bottom right position, which means that the superblock position of the superblock thread itself is at a position that is more than 2 superblock rows below that of the frame that we were just looking at, right? So this superblock distance is very big, and this is notwithstanding things like actual downward pointing motion or other post filters or tile threading, each of which make this even worse, right? So if you look at a superblock distance and you divide that by the size of the frame, you see that the maximal thread concurrency in frame threading, because of this problem, is only 3.6, and that's not very cool. Now, you can increase this by reducing the superblock size, the loop restoration size, but if you do that, you incur a significant quality loss of 1.5%, and we don't really want that. This is another one of those oversights. It would be nice if the encoder actually, if the reference encoder had actually supported all of these multi-threading types, because then hopefully we would have seen rectangular loop restoration units, which is the best of both worlds. It gives minimal quality loss and it gives the same maximal concurrency. More general point here being is that there are some users that are happy to wait 100 seconds to encode one frame, or at least spend the CPU cost on that. But they don't actually want to wait 100 seconds, right? Multi-threading is a must. And for multi-threading to work in the best possible way, the reference encoder should support all of these multi-threading types, at least in a skeleton form, to formally verify that they all work correctly and that you can get the maximal performance out of them. I'll leave it at that. So happy to answer any questions if you have.
Does anybody have the microphone?
Does your encoder include in SuperRes?
No,
Any reason? Any reason?
we haven't gotten to that feature yet. We implement almost all of the features, but SuperRes is one of those that we push to the very end. We will implement it.
There was a chart on decoder FPS. I missed. What is the resolution?
1080p.
Okay, thanks.
This one, right? Yeah, that was 1080p.
Volga?
Quick question: the BD rate charts that you showed for the encoder, are those by VMAF?
Yes.
How about for PSNR?
PSNR, there are gains, but they are smaller. They're like in the couple of % range currently.
Okay, thank you.
Anybody else? Okay, Ronald, thank you very much.
Thank you.